Hello everyone, and welcome to a Calc 2 conversation on an introduction to power series. In this conversation, we want to take a deeper look at some of the unifying theory that brings together all of the different series that we've been talking about. For example, if I look at these four series that I have right here, one thing I can observe that is common between all of them is that they all seem to be the same sort of structure. They all seem to be geometric. They all seem to have 5 to the n in the bottom. The only thing that seems to change is the numerator. So what I'm inspired to do in this conversation is to realize that all of the unique series that we've been talking about for the last several sections in Chapter 9 have actually been instances where we have taken a single function, like the one we have down here, and the function that we're looking at is actually one for which, when we take the variable x and we evaluate this function at different x values, we get different infinite series. So, for example, this series seems to just be f of -1, because that's exactly the entity that goes in the place of the x. Here we have a 2, a -7, and an 11. So here we have f of 2, here we have f of -7, and here we have f of 11. The only thing that's interesting about this perspective that we can adopt, well, not the only thing, there's lots of things that are interesting, but one of the most interesting right now is that sometimes this notion of function evaluation makes sense. For example, what we can see is that over here, these two are convergent power series. Well, we're eventually going to call them power series. These are convergent infinite series. Whereas over here on the right, we see that these are divergent infinite series. Specifically, the divergent geometric series. So as a result, if we adopt this perspective of letting these series all be function evaluations at specific points, we have to be really careful, because sometimes that point evaluation makes sense, i.e. we're convergent to a fixed number, whereas sometimes, on the other hand, we don't make any sense, and this function evaluation is ill-defined. So the name of the game here is, if this is a function, what's its domain? Well, let's go ahead and write this out in full generality. So the question we have is this. Given this function f, and notice now down here I've written it in full generality, I have it written as cn x to the n. So like up here, this example would have been, this was, for example, the series 1 over 5 to the n times x to the n. Looks very geometric in that way. Given a function that models itself like this, where in this instance, the Cn is allowed to be anything we want. In this case, it's geometric. It could be a p-series like. It could be something that has factorials in it, stuff like that. But as long as I have something that looks like the sum of some coefficient sequence times x to the n, that's what we have over here. That's this function. Notice that if I write this out in broad generality, what do I get when I plug in 0? I get c0 x to the 0, which is just 1. There we have it. If I plug in c1, I get c1 x to the 1. That's what we have here. Plug in 2, I get c2 times x to the 2. That's what I have here, so on and so forth. If I write this object out, now I have c0, c1, c2, etc. These x's seem to suggest that this construct that we've just built here seems to be a polynomial. But it's not just any polynomial, it's an infinite polynomial. And I note that right down here. So this function, which now we're going to look at and declare it to be an infinite polynomial, the main question we're interested in is, what is its domain? As we saw up here, for this infinite polynomial, -1 and 2 are in the domain, whereas -7 and 11 are not in the domain. We need to figure out what that domain is. One thing that we need to be a little bit aware of as we move forward is that this infinite polynomial here is written with powers of x. It is possible to take this polynomial, and if you think about your parent function transformations, you can take this polynomial and shift it, say, left or right. And in doing so, you're going to change the x's to, say, x minus 1 or something like that. And when I do that, as we can note down here, if I look at this quadratic, let's not even make it infinite, and I shifted everything to the left one, so this is all a shift 1 left. If I were to FOIL all of this out, let's see what I get. I get x squared minus 2x plus 1 plus 2x minus 2 minus 4. Regroup these terms, I'm going to get x squared with a 1 out front, plus it looks like 0x, because they all cancel, and then minus 3. So what I see is that when I change my polynomial to go from, in this case, base x minus 1 to, in this other case over here, base x, notice that the coefficients change. Over here on the left, I was working with coefficients 1, 2, and -4, and on the right, I work with 1, 0, and -3. So if I take a polynomial, even the ones we're familiar with, and I change the base to be shifted left and right, it will change the coefficients. So it stands to reason that in this case up here, if I take this infinite polynomial and I shift it left or right, these coefficients, the sequences that I had up here defining these series, will necessarily change as well. And as a result, when we introduce the next definition, we're going to be a little careful about where we choose to shift, or what we'll see, where we choose to center our polynomials. And now we're ready to introduce the topic of the remainder of this chapter. We're going to define, we'll do this one down here first, we're going to define a power series about a particular input. So this is going to be about x equals a, is going to be our infinite polynomial whose base got shifted over to a. So here's our c0 plus c1 x minus a plus c2 x minus a squared. More generally, we write it in this condensed form. Because we shifted over to a, we typically refer to a as the center, and the coefficients are the C1, C2, C0, etc. And if instead I choose to expand my power series about 0, then we get a series that looks like this, with one really important caveat. As we saw with this example up here, when I change my shift, my coefficients might change, so these coefficients might not be the same. In fact, almost always they're different. And so, the name of the game now is, let's try to understand some examples of power series, and let's try to understand, again back up here, what their domains are. When do they converge? When do they diverge? And just like we did back earlier in chapter 1 or chapter 9, when we looked at the first infinite series of interest, the geometric series, That's going to be our sort of starting point for this conversation as well. So to that end, let's start with the most basic power series I can come up with. That's going to be the series of just x to the n. So here what you might notice is the Cn here is just a 1. What that means is the overall series is just 1 plus x squared plus x cubed, etc. forever. But of course, if I change those x's out for r's, then you might recognize this. This right here, the series of just r to the n, as n goes from 0 to infinity, that's just a geometric series. And in fact, this is convergent if r is less than 1 in absolute value. So, inspired by that, we observe that this function that I have right here, so we're going to say, note that f of x equal to this function, this infinite polynomial, is just a geometric series with common ratio x. In particular, this converges when the absolute value of x is less than 1 and diverges when the absolute value of x is greater than or equal to 1. Now comes a small tutorial in something that you would have learned a while ago, but maybe it's been a while. In fact, this conversation is best had up here in the margin. Let's talk about absolute value real quick. When I talk about the absolute value between, say, 3 minus -2, many of you would sit here and say, oh, the answer is 5. Why? Well, 3 minus -2 is 5. Absolute value of 5 is 5. But the correct way to interpret this is not as it turns everything positive, but you should really think of this as a distance calculator. This is really asking, what is the distance between 3 and -2? If I draw this on a number line, -2, 3. Between that I have a 0, a -1, a 1, and a 2. So if I start at -2 and I end at 3, what's my distance? We have 1, 2, 3, 4, 5 jumps. So the answer to this question should be 5. That's what the absolute value is technically computing. So for example, if I wanted to compute what's the absolute value between A minus B, you should think of that as always the answer to the question, what is the distance between, in this case, not 3 and -2, but now it's going to be between A and B. And this pictorial representation we're going to build here is going to become very, very, very important. And so over here, if I come down here and I look at the absolute value of x being less than 1, how are we going to interpret that? Well, technically speaking, this is the same thing as absolute value of x minus 0 is less than 1. And if I borrow my new interpretation, what this means is that I'm asking, when is x, we'll do it this way, for what x values are they 1 unit of distance away from 0. That's what that's asking. So if I reinterpret what I have so far, what do I have? I have the geometric series so far, common ratio x. I said this converges when absolute value x is less than 1. That is when absolute value x minus 0 is less than 1. So to recap, this converges when absolute value x minus 0 is less than 1, or that is when x is at most 1 unit away from 0. So if I draw this pictorially, here's 0. I want all x values, that one, this one, this one, that one. I want all of them that are at most 1 unit away from 0. So if over here is -1 and over here is 1, then everything in between is fair game. Because all of those are less than 1 unit away from 0. Right? This distance right here is absolute value x minus 0, for example. And maybe now you can get a better picture of why earlier we referred to this A as a center. This 0 is a center because it's literally the center of this interval at which this function is converging. So the answer to our question earlier, we said, what's the domain of this series? Apparently it's -1 to 1, because I know I converge in that region and I'll diverge outside of it. So we'll make that note as well. Since this is a geometric series, it diverges at the endpoints. X equals -1 and 1. It'll diverge at those endpoints explicitly because of what we saw here. It diverges when x is greater than 1 or when absolute value x is equal to 1. That means when x is 1 or -1. So anytime I have a geometric series like this, a geometric power series, it'll converge in this range and it'll diverge elsewhere, including the endpoints. So this is the answer to, hey, here's a function. What is its domain? It turns out that I can do that by looking at this sort of distance interpretation of the absolute value. And that'll give me a good picture to work with. So anything inside this region will cause this power series to converge, and anything beyond it will diverge. Why is this so powerful? Why are we talking about this right now? Well, oh, you know what? Before I get too ahead of myself, by the way, if I wanted to change up this diagram, right? In the spirit of what we've been doing here, I could talk about things like what's the absolute value of x minus 3 less than, say, 2. The way I want you to think about this is I want you to, again, think of this as your center. And what we're eventually going to do is call this a radius. Because the picture you should have in mind is that you start at 3, and then you're allowed to go a unit 2 in either direction. Meaning you're allowed to go down to 1 or up to 5. So this statement right here turns out to be equivalent to the interval 1 to 5. And we're going to need to adopt that perspective fairly soon. And you can see now why I call this my center and maybe why I call this my radius. Because it seems to be building some sort of like circle of some sort, if I imagine this in 2 dimensions. more on that later. Before I get too much deeper in that, I do want to stop and highlight the important part of what we've discovered. What we just noticed is that specifically, as long as I'm inside the region I've considered, then we know that this series converges. But what does it converge to? Well, what we have is that on one hand, we write it all out, and it's clearly equal to 1 plus x squared, etc. We did that earlier. But on the other hand, this series starting at 0 is a geometric series. So if it's going to converge, so big if over here, then we know it's equal to the first term, 1, over 1 minus the common ratio. And so what that tells me is that if I live inside of this interval, which again, like we saw earlier, this is the same thing as saying x is in -1 to 1, exclusive, then it turns out that this function here, 1 over 1 minus x, is literally equal to this polynomial. And this is fascinating because this function has a vertical asymptote, which is very, very poorly behaved. A polynomial is one of the best behaved things you can possibly find. So this approach that we have is allowing me to take bad functions that misbehave and replace them with beautiful functions. The price that I pay is that the beautiful function needs to be infinite, which means we need Calc 2 to understand convergence, divergence, etc. But this approach is really great because if this is modeling some sort of a system I'm working with, I don't need necessarily the full sum. If you think about like the alternating series error estimation, I can take a partial sum, and sometimes that's good enough. I can't stress enough in this entire dynamic how important this if is right here. This agreeance right here is absolutely predicated on taking x values in this region. Let me show you what I mean. What if I took this situation, but I put in, let's take something outside this region. Let's take x equals 2. Let's see what this equation is telling me. This equation is telling me that if I add up all the powers of 2, which is this series here, according to the identification up here, that should be equal to 1 over 1 minus x. So here we have it, 1 over 1 minus 2, which is clearly a -1. So if I add up a bunch of positive things, I got a negative number. I want to say that again. Positive, negative. Hopefully, you agree that's nonsense. This clearly can't be true. And indeed it's not. This will not work. In particular, this is failing because x equals 2 is not inside of this domain, right? The problem that we have here is that this choice, x equals 2, is not in -1 to 1. So that's what's causing a problem. So you do have to be very, very careful about when you put in, what numbers you put into your series in order for it to either make sense or not make sense. Now, this is an example of a series that we said it looks like the center was at 0. And that's what we were talking about up here. This is a first type of power series. Let's look at one where I shift the center a little bit. So here, I have this power series. Again, power series all look like this form. The sum of Cn x minus a to the n. So I see that these are my Cn's, and my a seems to be a 2. This is a power series, and I want to know what its domain is. That is, I want to know what are the x values for which it converges. Let's talk about it. So the first thing I'm going to note is the following. This series, if I start here at 0, write -1/2 to the n times x minus 2 to the n, If I were to kind of consolidate this all under the same power, I would get a negative x minus 2 all over 2 to the power of n. This is a geometric series. That entire thing on the inside, that is its r value. That's the common ratio. So this converges when, of course, the absolute value of r, so in this case, the absolute value of negative x minus 2 over 2 is taken to be less than 1, which of course kills the negative. I get absolute value x minus 2 all over 2 is less than 1, and therefore I get absolute value x minus 2 is less than 2. Now please, please, please do not move this negative 2 over. You can't do that. These absolute value bars are like parentheses. They have to stay there. But this form is very much like this example up here that I was talking about, where I had a center that was at 3 and a radius of 2, and this was the picture. This is almost the same thing. Here I'm working with a situation where I have my my center is equal to positive 2, because the negative is always inherent in the absolute value, and the radius is a 2. So if I think about that picture, again, the center and then the radius, then what I'm working with is the following picture. I center myself at 2. I go 2 to the right, giving me a 4. I go 2 to the left, giving me a 0. And that entire region is exactly what I'm looking for in terms of convergence. So this series is convergent on at least 0 to 4. The only question is, what about 0 and 4? What about those endpoints? But like we saw last time, specifically, since this is a geometric series, we know that the endpoints diverge. So we converge on, it looks like 0 to 4. And we converge to what? It's going to be 1 over 1 minus the common ratio. That's negative x minus 2 over 2. Let's see, that's going to be keep, change, flip. So we'll get 2 over, it looks like 2 plus x minus 2. So it looks like 2 over x. So this series right here is apparently a power series for 2 over x, and it converges between 0 and 4. And so this notion of finding the domain of this series right here, this is the set of numbers for which I converge, the interval over which I converge, we can now give that a name. Let's go ahead and formally refer to that as the interval of convergence. And then, borrowing from the phrase that I kept using, radius, we're going to refer to that radius as the radius of convergence. And so the picture that I have in mind there is if I'm working with something like absolute value of x minus a is less than r, I'm working with a real number line, a center of a radius of r taking me to, say, a plus r, a radius of r over here taking me to a minus r. And like I alluded to earlier, you can envision this as some sort of a giant circle where indeed my radius is this r that I have over here, the center is a like I have over here, and that kind of motivates, or maybe I should say justifies, this choice of naming system. And so based on the examples, by the way, it is worth noting, as long as I'm within this radius of convergence, in particular, the convergence is absolute. So this really is as pretty as it gets. Now, what we saw up here is this was a power series seemingly centered at 0. This was a power series seemingly centered at 2. The real question I have is, these are geometric-like. That's how we were able to use this formula right here. What happens, and I asked this question down here, what happens when my power series are not geometric-like? Well, I know I still converge sometimes, so how do I know when I converge? It turns out the answer is, well, instead of using a geometric series type approach, we simply use a better tool. But it has to be a tool that uses and implies absolute convergence, and there's really only one catch-all tool that does that, namely the ratio root test. That turns out to be really useful for determining the radius of convergence, and then, as we've seen so far, we've spent extra time asking what about the convergence of the endpoints. Whenever we were geometric, we know the endpoints diverge. In broad generality, we do have to check them separately. So let's look at some examples of finding the radius of convergence using the ratio or the root test. We'll start with this one. This series is a power series. What we see, for example, is that this is my x to the n. It seems to be centered at 0. And my Cn is everything else. So let's go ahead and just not think too carefully about this. Let's just go ahead and hit, say, let's do the root test on this. This means I'm going to compute the limit as n goes to infinity of the nth root of the absolute value of an. That's everything. So this is the limit as n goes to infinity of the absolute value of -1 to the n minus 1, x to the n over n, all to the 1 over n. The absolute value, of course, will kill the -1 to the n, so we'll be left with the bottom is an n. Well, it looks like an n, say, to the nth root. And interestingly, what happens at the top? The -1 gets killed by the absolute value, but this x, I actually don't know if that x is positive or negative, so I can't quite drop the absolute values. It does still persist on the x. But I will say that the 1 over n cancels with its n. So I'm left with that decomposition. And you may recall, based on what we did in the previous sections, that the nth root of n does limit to a 1 as n goes to infinity. So this overall limit, which is an n limit, causes the denominator to go to 1, but the top, x, well, that has no n's. So as far as the n limit is concerned, the x stays the same. So that just stays. And if I zoom out, okay, the root test. The root test says what? The root test says that this converges absolutely if that limit, which we just saw as absolute value x, is less than 1. So frequently the way I like to write it is I like to write less than 1, and I like to say convergent if. But of course, what is this? This, as we saw on the previous page, is the same as absolute value x minus 0 is less than 1. So I can look at that, and I can envision this as an example where I have a center, and I have a radius. So there you have it. I now know what my radius is. I can draw a picture, drop in a 0, go to the right one, go to the left one, and everything in between is at least in my interval of convergence. By the way, I'm going to use a shorthand moving forward. When I talk about an interval of convergence, I'm going to write the interval of convergence as IOC. So down here, what I can observe is that, so the interval -1 to 1 is in the IOC, but it may yet still converge at those endpoints. So we do check those separately. So we're going to check those endpoints. If I check x equals -1, I plug that into the original series. I end up with the sum -1 to the n minus 1 times -1 to the n over n, which it looks like this is just -1 over n. This is, of course, a divergent p-series, divergent harmonic. Whereas if I wanted to try out x equals +1, we get the series, it looks like just -1 to the n minus 1 over n. And this is convergent, it's actually conditionally convergent by the alternating series test. So the IOC apparently is, well, it's supposed to be -1 to 1, but apparently I'm divergent at -1, meaning I exclude it, and I am convergent by the alternating series test at 1, which means I include it. And this becomes the main process for doing this. It's mostly just apply the ratio root test, interpret that as the geometric understanding of distance, then check your endpoints separately. Let's do another one. So here I have -1 to the n minus 1, x to the 2n minus 1 over 2n minus 1. I used a root test before. Let's use the ratio test here. No, actually it might be easier to use the root test because the bottom's a polynomial. So let's find out. So we're going to do another root test. So we're going to look at the limit as n goes to infinity of the nth root. Well, this is going to give me the nth root of absolute value. It looks like -1 to the n, x to the 2n minus 1 over 2n minus 1. So of course, what's going to happen here, we're going to get the limit as n goes to infinity. The absolute value will persist onto the x, like we saw above. The 1 over n root will hit the exponents, giving me a 2 minus 1 over n. And then on the bottom, we end up with an nth root of 2n minus 1. And just like we saw before, here, if I zoom in, the denominator is going to go to a 1, just like we saw before. But interestingly, the 1 over n pizza tricks and goes to 0. So here, what we're going to be left with is absolute value of x squared. That's a different problem. And as I saw in the previous problem, this is convergent if. But of course, if I square root both sides, I get absolute value x less than 1. And so it's almost the same as the previous problem. So what we can say is that the IOC is at least, as we saw in the previous problem, this interval from -1 to 1. But what about those endpoints? So -1 to 1. What about those endpoints? Let's check them. Now, if I choose my x to be -1 endpoint, then what do we have? We end up with, let's do it down here, we're going to end up with the series, it looks like -1 to the n minus 1, -1 to the 2n minus 1 over 2n minus 1. And it looks like for this, we're going to end up in a situation, let's see, the power of 2 kills the -1, so we're going to end up with just the sum negative 1 to the n over 2n minus 1. And this is conditionally convergent. So we'll put that in pink. This is going to be conditionally convergent by the AST. And if instead we chose x to be a 1, we get the series, it looks like negative 1 to the n minus 1 over 2n minus 1. And it looks like here we're conditionally convergent again. We're convergent by AST. So that means that the interval of convergence is picking up both endpoints. So we're going to get bracket negative 1, bracket 1. So here we have an example where we're getting the interval of convergence to be both endpoints, instead of the previous example where we had only one endpoint. And then the geometric ones we saw earlier, we got no endpoints. But the process is all the same. Here we're using the root test. We could have used ratio. We do that. We find our center radius. We draw a picture, check those endpoints, figure out your interval of convergence. Let's do two more examples, because these will highlight some weird edge cases we need to care about. So here I have the series x to the n over n factorial. Because I see a factorial, the root test is out of the question. We're going to hit this with the ratio test. Here I'm going to look at the limit as n goes to infinity of absolute value an, which is x to the n plus 1 over n plus 1 factorial, divided by that's an plus 1, divided by an, which is just keep, change, flip. It's going to give me n factorial over x to the n. If I simplify this, I'm going to get, it looks like absolute value x over n plus 1. Of course, the bottom is positive, but the x might not be, so the absolute value will persist upstairs. And what we see here, again, this is an n limit, so the bottom is blowing up, but the top, just a measly x, has no bearing on the limit, so this is actually going to get pizza tricked. So this is actually going to be a 0. Notably, that is less than 1, but importantly, that is true for all x. There are literally no x values that won't do this. I could make x be a 49 and this limit 0. Make it a negative 2 and the limit 0. Make it a pi and the limit 0. So that means no matter what x I put in here, this thing will converge by the ratio test. So we are convergent for all x values. Therefore, or I'll say hence, the IOC is everything. It's the whole interval, negative infinity to infinity. It's the easiest thing to compute. So this is what happens when you do the ratio root test and you get a 0 for everything. It's actually much less work than the previous two. But if I kind of flip the script a little bit, what if instead of putting the n factorial on the bottom, I put it in the top with the x to the n? Let's see what happens. Here, I'm going to observe that by the ratio test, if I look at the limit as n goes to infinity, in this case, I'm going to get n plus 1 factorial x to the n plus 1, that's over an, which is just n factorial x to the n. Again, I'll simplify this a little bit. I'll end up with n plus 1 times absolute value x. Here, instead of getting pizza tricked like before, this n plus 1 really wants to blow up to infinity. And in fact, it will. No matter, it seems, what this x is, this n plus 1 will surely blow this up to infinity, which is of course larger than 1 and hence divergent. Except one magic point. This is true for all x which isn't 0. If this x is a 0, then that kills every single one of these terms every single time. So this limit will become a 0, which is less than 1, as we saw. So what that actually means here is that when x equals 0, we are convergent, but we diverge otherwise. So what that means is that the interval of convergence is, if we drew a picture, up here we said it was literally everything from negative infinity to infinity. Here it's almost the polar opposite. At 0, we literally pick up 0. That's all we get. All of everything else is divergent. So what we write this as is we use a little curly brace, we put the center in it, and then we call it a day. These examples, the two complicated ones in the beginning, and then these two simpler ones at the end, demonstrate the three possible scenarios you can consider. Given an arbitrary power series, like what we have here, three things can happen. 1. There exists a radius so that you diverge beyond that distance from the center, but you converge absolutely when you are within the distance from the center. And then you may or may not converge at the endpoints. You have to check that separately. Or you converge absolutely for every x, i.e. your radius is at infinity. That's what we saw up here in case 3. Or lastly, the series converges only at your center. That's what we saw right here. And it diverges everywhere else. So your radius is a 0. And that is all of the options that you have for a power series. Now, we've covered a lot in this video. We introduced the notion of a power series. We talked about some vocabulary of the fact that it's an infinite polynomial, where the main goal is what is its domain. We said that we can center our power series, our polynomial, at different points depending on horizontal shifts. And then we looked at some examples. We looked at a few geometric-like series where we were motivated to care a little bit deeper about this geometric understanding of the absolute value. And we looked at some deeper examples of the geometric series here. We talked a little bit about how you have to be careful about your interval of convergence, because if you're not in your interval of convergence, you'll end up spitting out nonsense. And then lastly, we talked about using the ratio root test to compute your radius of convergence, and hence, after checking endpoints, computing your actual interval of convergence, where we saw with the geometric that we excluded those endpoints. But we saw that when we don't have something geometric, we may very well pick up one or both of our endpoints. The rest of this section, and the subsequent video on this content, basically has us look at a wider variety of power series and asks, how do we make more power series? We have geometric ones, we have these ones that we were working with, but the question becomes, hey, if this power series represented that function, what if I have a function I'm interested in and I wanted to find its power series? Here, I already knew what the power series were. But how do I know what they converge to? What function are these approximating? In general, that's a hard question to answer, but we're going to look at some examples where we'll start with chosen functions like what we have here, and we're going to see if we can't use some algebraic shenanigans to compute and find associated power series for given functions we're interested in. And that's what the rest of this handout's going to cover. So please take a look at that whenever you get a chance. If you have any questions, let me know. But otherwise, have a great rest of your day, and I look forward to continuing this conversation with you next time.